A best practice for building safety-critical systems is to use the doer-checker architectural pattern. Allocate the main functional requirements to a low-sill doer and allocate safety requirements to a high-sill checker. An example of this might be a speed limit for a vehicle. The doer can deal with providing smooth acceleration, optimizing fuel consumption, and so on. And the checker can simply be watching to make sure that the maximum safe speed for the vehicle is not exceeded. The doer can do whatever it wants as long as it does not violate the speed limit, and the checker is there to keep things safe. Using this pattern often requires rethinking the notion of safety to create a safety envelope approach. However, this rethinking pays off by reducing the scope of how much of the system must be developed to high-sill levels of engineering rigor. Next, make sure you have good safety requirements. They should trace to system-level safety goals and be orthogonal to normal functionality so that you can get a clean separation between the doer and the checker. This separation approach can make safety simpler to validate than an integrated system approach because safety can be determined by validating just the checker, including testing, peer reviews, and other software quality techniques. Because the safety functions have been allocated to the checker, testing for safety largely involves exercising the checker box and making sure that you didn't miss anything using your engineering process. Some system testing is also appropriate to find missed nuances in requirements and so on, but in general, the checker itself must be the thing that maintains system safety. As with any approach, there are some pitfalls and trade-offs. The first pitfall is that making the safety envelope simpler to check can cost ability to optimize. This is an intentional trade-off that sacrifices the permissiveness of the safety checker to keep things simple. Put another way, using this architectural pattern gives up your ability to operate in the irregular regions near the safety boundary, but in return, what you get is a system that is much easier to build and demonstrate safe. A consequence of this trade-off is that if you want to make the doer more complex and more aggressive at the boundary of safety, that's going to increase the complexity of the checker to increase permissiveness. The other big pitfall is that a doer-checker pair is a fail-silent architectural pattern. If your system requires fail operational functions, you're going to have to use either multiple doer-checker pairs or more sophisticated safety architectural patterns.